Hello, I would like to welcome you to the next talk, which has the goal of making current and near-term quantum annealers more useful for combinatorial optimization. So in particular, it addresses a major bottleneck, which is that of finding minor embeddings for quantum annealer topologies, such as the current Chimera or the next generation Pegasus connection topologies of D-Wave quantum annealers. This is joint work with Stefanie Zbinden from ETH Zurich and Hristo Djidjev and Stefhan Eidenbenz from Los Alamos National Laboratory. You can find my picture and contact details here, because unfortunately I am not able to join by webcam. So first I want to dive right in and address the question, what is or what does quantum annealing? So in a quantum annealer, we basically have a lattice of programmable superconducting qubits on which a Hamiltonian acts. The initial Hamiltonian is simply a transverse field, and from there we anneal to, we can think of this as like crossfading into a final Hamiltonian, which is this Ising Hamiltonian. So why would we do this? Well, the initial Hamiltonian has an easily preparable ground state, which is simply the superposition of all basis states. And since qubits there are not entangled, we can easily prepare this ground state. Now the hope of quantum annealing is that if we do it correctly, we can reach the ground state of the final Hamiltonian, or one of the ground states of the final Hamiltonian. And such a basis ground state would minimize this quadratic function here. Now these local fields here, these HIs, can be applied to every qubit, but these couplers here are restricted to available couplers in the host topology. So here we can see an excerpt of the Chimera host topology, and we can see that there are actually not that many couplers and only between kind of neighboring qubits. So what is quantum annealing used for? Well, recently it was very successfully used for quantum simulation to study topological phenomena and phase transitions. However, for the original motivation to build these quantum annealers, combinatorial optimization, there remain a lot of challenges. First of all, there's a strong classical competition, but on the quantum annealer side, there are several bottlenecks. And one of them is the minor embedding, which relates to this restriction of couplers being only available on the host topology, and this is what we're going to look at here. So therefore, we'll first look at how to solve combinatorial optimization problems with quantum annealers and what the workflow thereof is. And then we address the arguably major bottleneck, minor embeddings. Then we look at the large-scale experiments on embedding algorithms that we ran, what we studied and what I will focus on in this talk, and the main results. Finally, I give a brief description of the two algorithms that we propose, Clique-Based MinorMiner and Spring-Based MinorMiner, before giving a summary. So for combinatorial optimization on quantum annealers, there are many steps. So first we start with a quadratic unconstrained binary optimization problem, and this is really quite general, because if we have a constraint optimization problem, we can pack linear constraints into quadratic penalty terms to get an unconstrained problem. Now, if we substitute for the variables x here, then we get the Ising formulation. And this now already looks very similar to what we had before as the ground state of quantum annealing. What is important in this transformation is that these couplers Jij are non-zero if and only if the Bij were already non-zero. So these non-zero values, they define a problem graph P. For example, here this problem on 4 variables Z1 to Z4 will have this problem graph P here, where each of the couplers 1, 1, 1, and 1 here results in an edge of the problem graph. Now, when we have a problem graph P and the host graph H, then we need to embed this problem graph into the host graph. But there is a challenge, because the problem graph here has a triangle but the host graph is bipartite and therefore has no triangles. So the idea is to represent a node or variable here by multiple qubits or nodes in the host graph. So this variable here gets mapped to a chain of qubits. So this procedure is called finding a minor embedding. And then we need to set parameters accordingly. We need to adapt the local fields, and we need the ferromagnetic coupling here to push these qubits into taking the same value when we run the annealing. Then after we've adjusted all of this, we anneal with the corresponding Hamiltonian, get a result, and have to translate this back to the original problem to get a solution. So how do we find minor embeddings if not by hand? There are basically two major methods here. The first is using known clique embeddings. So here we have a clique of size 12 and an embedding into a chimera graph, and we can see that every node here gets mapped to an L-shaped chain. And because all these L-shaped chains cross, the edges between nodes here will be represented somewhere by a coupler between chains here. However, that is good for cliques and subgraphs thereof, but that's only good for dense graph because it fills up the host graph very fast. It has a quadratic scaling. So if we have more nodes but a sparser graph, like this 16 node 7 regular degree graph here, then we use heuristic embeddings to find a minor embedding. So the question is really, what are the largest QUBO problem graphs we can still embed, both in terms of the number of nodes as well as in terms of edge density. And we ran large-scale experiments with a few 100,000 data points, and I will show you the study parameters of these experiments next. So first we have our two host topologies, the currently available Chimera, which consists of axis parallel rectangular qubits with couplers between intersecting qubits and between end adjacent qubits. So this gives rise to a 2048 qubit graph. We show only an excerpt here, where the nodes have degree 6, and we have 16 times 16 bi-clique K44 cells. The graph is bipartite, and there is a known 64 clique embedding. Now the next generation, which should come out somewhere this year, has more qubits, but even more importantly, the rectangles got longer, which results in a higher degree because we have more intersection and now also couplers between neighboring parallel qubits. So this Pegasus P16 graph has a known 180 clique embedding, and also odd cycles such as 3 cycles and 5 cycles. Now, for the problem graphs, we want them to represent a large variety of potential QUBO problem graphs. So we went for random graphs, and most famously the Erdo GNP graph model, where each edge is drawn with probability p. So here we see a 20-node GNP with edge probability 20%. So this gives a binomial degree distribution. Next, we look at Baraba-Albert graphs, which are used to model social networks, where newly joining people have a preferential attachment to already well-connected nodes. So, for example, this node attached to these highly connected nodes. So this gives a power law degree distribution. And finally, we looked at random d-regular graphs, where each node has the same degree d, here for example degree 4, and where we have a constant degree distribution. So overall, our study parameters look like this. We have our 3 QUBO classes, our 2 host graphs. As an existing heuristic, there's MinorMiner, which is the heuristic that is provided by D-Wave and is open source for its quantum annealers. There's the layout-aware MinorMiner approach, which was introduced last year at ISC, which is suggested for Chimera for QUBOs that come with a natural problem-specific plane drawing. And there are our two algorithms, spring-based and clique-based MinorMiner, which build on MinorMiner. So MinorMiner is known to work comparatively well on Chimera, but no longer on Pegasus. And that's why we focus on Pegasus, because this next generation topologies will have a need for better embedding methods. We also focus on Erdo-Shreni graphs, but the results are similar across these three types of graphs. We leave away layout-aware MinorMiner because it's only competitive on Chimera. So here let me explain how our experiments looked like. So we tested a large variety of node ranges. So here we tested every possible number of nodes up to 425, and that single steps of edge probabilities on the y-axis. So for every data point in here, we sampled 5 G and P graphs, and then we checked whether MinorMiner in its standard configuration was able to embed this graph. This red line here denotes the best known, the limit of known clique embeddings at 180. And we can really see that MinorMiner, for a huge range of dense graphs, does not even get close to the known clique embeddings, which was surprising to us because it's known to do that on Chimera. So our goals are twofold. One is we want to push to the right beyond this existing knowledge of clique embeddings, and down here we want to push to the right and above this green tail of MinorMiner. So the same we also want to do for Baraba-Albert graphs, where we have increasing edge density on the y-axis with increasing growth parameter m, and the same for regular degree D graphs, where on the y-axis we have the degree D. So now let's go to Clique-Based MinorMiner and see what changes. So as we can see, we have a huge improvement here for dense graphs, and we were able to go beyond this known clique embeddings. But if you look closely, we made things slightly worse on sparse graphs. So we also want to fix that. And for that, we introduce spring-based MinorMiner. So if we transition to the result from spring-based MinorMiner, we can see that here we extended the range. And this is especially noteworthy here, where the ranges go now up to 1,000 nodes and beyond for very sparse graphs. And what we can also see is that somewhere here we have a sharp transition threshold, where above clique-based MinorMiner clearly outperforms spring-based MinorMiner, and below spring-based MinorMiner outperforms clique-based MinorMiner. So we can summarize this by comparing a dual approach of clique-based MinorMiner and spring-based MinorMiner versus the maximum best possible previously. So above this blue line we ran clique-based MinorMiner, below we ran spring-based MinorMiner, and we benchmarked this against the best known embeddings with previous methods. And what you can see here, a very dark green denotes that our approach managed to embed all 5 graphs, while the previous approaches managed none. So this color gives you the difference between our approach and the previous approach. So only at these very few purple data points can we see that we're slightly worse than existing algorithms. And here we have a huge bunch where we do much better, and for Barabasi-Albert graphs and regular degree D graphs, which can get much sparser than Erdo-Shreni graphs, we see that we can extend the ranges for several hundred, or roughly 150 nodes in the very sparse regime. So now I want to talk a little bit about how these algorithms look like very briefly. So in terms of the existing algorithms, this red line, which denoted the known clique embeddings, where we have L-shaped chains, this is the same for Pegasus as well. These clique embeddings are quickly computed, but as mentioned, the problem is that the problem graphs P are quadratically smaller than the host graph H. Then D-Wave's heuristic MinorMiner works as follows. It starts with a possibly empty set, which has, if it's not empty, possibly overlapping initial chains. And then there are two phases. In the starting phase, there's a single loop over all chains, where each chain is replaced, and in the end of this starting phase, all edges of the problem graph P are represented by couplers between chains in the host graph. And then it goes to a randomized fixing phase, which is time limited, where we repeatedly replace chains by smaller chains until they are no longer overlapping, or until we run into the time limit. So our approach with spring-based and clique-based MinorMiner is to change these initial chains. So we try to give good initial chains to improve upon MinorMiner. So for clique-based MinorMiner, we assign the L-shaped chains of a clique embedding to 180 nodes of the problem graph P, and the other nodes get empty chains. Now if P is dense, we assign the chains to low degree nodes. The purpose of this is that once our clique-based MinorMiner introduces the nodes of high degree, that they have good connection possibilities to the already proposed initial chains. But if P is sparse or medium dense, then we assign chains to random nodes. We tried many other assignments. We tried splitting up the L chains, assigning chains multiple times, but all these approaches were outperformed by these very simple assignments here. For spring-based MinorMiner, we focused on a drawing-based approach. So we compute a Fruchtermann-Reingold force-directed graph drawing of the problem graph P in the Euclidean plane. And important here is that we have edges. Whenever we have an edge E in the problem graph, then we have an attractive force which scales proportionally to the inverse of the product of the degree of the two nodes. So this gives this attractive force as a purpose to give adjacent nodes of high degree enough space. So they should be spaced sufficiently far from each other. And then we overlay this drawing with the existing drawings of the host graph, and we map nodes, drawn nodes of the problem graph P to closest nodes in Euclidean distance of the drawn nodes of the host graph H. And this tuning here, as I said, is really important. For example, layout-aware MinorMiner is agnostic to degrees of adjacent nodes, and this explains why it doesn't extend its performance to Pegasus. So finally, I'd like to come to the summary. So here are the raw numbers. For dense QUBOs, so these are basically QUBOs which have an H density of above 8%, the clique-based MinorMiner algorithm clearly outperforms the other candidates and the existing ones. So here we have like 8,000 additional QUBO problems that it was able to embed. Then for sparse QUBOs, the leading contender is spring-based MinorMiner. Again, it beats out all other approaches. few notes on this as well. The Clique-Based MinorMiner even found clicks up to 185 nodes, which is remarkable, and I think the best known so far. And this Spring-Based MinorMiner also performed well on Chimera and was slightly better in combination than the existing algorithms. Also, there were regimes where this was not true and the picture is less clear. But overall, Spring-Based MinorMiner also performed really well on Chimera. So we can try to map this. So we kind of flip our picture and now have the parameters on the x-axis. So basically, for each edge probability p, we want to know how many more graphs or how much larger graphs we were able to embed. So in orange, we show how much more Spring-Based MinorMiner added to the picture. And in blue bars, we added how much more Clique-Based MinorMiner added to the pictures. So we can see here we have a double-digit increase in the number of nodes a QUBO can potentially have, and also up to 10% if we look at the additional range in percentage over all existing QUBO graphs. The picture is slightly similar, but also slightly different for Baraba, Albert graphs, and D-regular graphs. So here, the Spring-Based MinorMiner adds a huge number of larger graphs that can now be embedded. So this is the difference between these two and GNP graphs, is that they can get much, much sparser. And Spring-Based MinorMiner performs extraordinarily well on really sparse problem graphs. So QUBOs just don't get this sparse without getting disconnected. And then here the high percentage increase for high parameters is simply explained that there are not many graphs that exist in this regime at all. So even adding a few graphs makes a huge difference percentage-wise. So in conclusion, we suggest that making click and spring-based options available for the initial chain parameter of MinorMiner could be really helpful once Pegasus comes out. We also have future work which we would be interested in to do. So we'd be interested in doing case studies of real-world QUBO instances instead of just random graphs. We would like to include other host graphs, for example, from CMOS annealing architectures. They have their own proprietary software, which is not open source, at least not at the moment. And we would also like to consider metrics beyond embeddability, like the distribution of chain lengths and time to solution metrics. With that, I would like to thank you for your attention, and also thank you to all the sponsors that made the virtual conference possible.